Okay, so today we will start from page 9 of set 6 on the periodic table. So we'll finish up with some interesting developments and trends in the periodic table, which are not strictly part of the O-level syllabus, but can be tested in your database questions, as well as it's good knowledge for you in general. So the periodic table was developed over many, many years. Not just one person worked on it. You're talking about many, many people's work. So it all started with looking for patterns, trends in the periodic table. So the German chemist Dobereiner had started to look and saw similarities in certain elements based on their properties. In particular, he noticed that groups of 3 elements, triads, he called them triads, had similar chemical and physical properties. Moreover, he did also notice that the atomic mass of the middle element was approximately the average of the atomic mass of the other 2 elements above and below it. So take, for example, he saw lithium, sodium, potassium formed a nice triad. And he realized that the middle element, which was sodium, had an atomic mass that's the average of lithium and potassium. So you can take a look. 23 is the average of 7 and 39. Okay, so that's how he came up with what we call the law of triads. So you realize that lithium, sodium, potassium, it formed a triad. Then you had calcium, strontium, barium. Then you had chlorine, bromine, iodine. They kind of form a triad. So of course, now with the benefit of hindsight, if you look back, do the Dobereiner triads remind you of the modern periodic table? I hope the answer to this is yes. The triads resemble the groups, right? It resembles the arrangement of elements in the groups. Specifically, groups what? Okay, so firstly, we have group 1. Okay, so I have to write the group numbers in 2 ways. Okay, so for the older syllabus, we use Roman numerals. For the new syllabus, the Sec 3s you are doing, you're just using numbers. So group 1, all right? Moreover, besides group 1, calcium, strontium, barium, they are found in group 2. Finally, chlorine, bromine, iodine, they are found in group 17 or group 7, okay? Now, you must use the correct version of the group number. So for the Sec 3s, you need to use the 1, 2, and 17. For the Sec 4s, you need to use the I, and VII. It's not interchangeable, all right? So the exam syllabus is different. So obviously, the triads do resemble your groups, okay? However, can you find examples of triads in the modern periodic table which will not follow Dobereiner's triads? I think the answer is obviously yes. Okay? The answer is obviously yes. Okay, you can think of so many examples of elements in the modern periodic table which do not actually follow this rule. So I'm just going to give one example. And this example, I will take it from over here. Let me just take a look. Yep. Okay, I'm just going to do copper, silver, gold. Okay, copper, silver, gold, you will realize that doesn't really follow the rule. Okay, copper has a mass of about 64. This is mass. Silver has a mass of 108. Gold has a mass of 197. So you realize immediately it's not true that silver is the average, right? It is not equals to the average of copper and gold in mass. Okay? If you were to take the average, 197 plus 64 divided by 2, it is not 108. Okay? So what are the examples that do not follow Dobereiner's triads? The one that doesn't follow the Dobereiner's triads are your transition metals. So transition metals do not follow Dobereiner's triads. Okay? So anything from period 4 onwards wouldn't follow Dobereiner's triads because there's the addition of the block of transition metals in the middle. All right? So that's the first historical development. Johann Dobereiner, a German chemist who saw some similarities and patterns in the elements and organized them into triads. He was observant. He managed to get some of the elements arranged correctly into the groups that we now know. Now, another chemist who was from England, the English chemist, John Newlands, came up with a slightly different law. He came up with the law of octaves. So according to John Newland, according to him, elements can be arranged in order of atomic mass. Wow. Today, the modern periodic table, do we still arrange elements by mass? The modern periodic table, though, does not arrange elements in order of increasing mass. The modern periodic table arranges elements in order of proton or atomic number. Okay, so I hope you remember this. The modern periodic table no longer uses atomic mass. We will use the atomic number, the number of protons, and arrange it in order. Okay, so the John Newlands arrangement is not what the modern periodic table uses. However, if you look at what John Newlands did, he arranged them according to mass, and he realized every eighth element of the row had similar properties to that of the first element. That means, if you were to arrange elements in rows, number 1 to number 7, the eighth element will be similar to the first. And that is total sense, right? Now you know lithium and sodium are similar. Similarly, potassium and sodium are also similar. Okay, so with the benefit of hindsight, you realize, oh, wow, this makes perfect sense because it makes sodium and lithium similar. It makes magnesium and beryllium similar. Similarly, chlorine and fluorine are similar. Okay? Of course. It was eventually dismissed because when you discover more elements and you try it out, it doesn't really seem to work. It was only accurate up to calcium. And if you think about it, this is where your chemistry teachers probably taught you until, right? You only know how to fill in electronic configurations for elements up to calcium. Why not beyond calcium? Why do you not know how to fill in electronic configuration for, say, iron, zinc? Why? It's because you have not learned SPDF at O level. You have not learned how to fill in SPDF, the electronic configuration according to SPDF. However, as part of Chem O, you did learn how to fill electronic configuration according to orbitals. All right. So it was only accurate until calcium because, of course, the problem is after calcium comes the transition metals. So it doesn't apply from period 4 onwards, again, because transition metals are found after calcium. So because of the addition of the transition metals as one block of elements, you no longer can say that every eighth element is the same as the first. Okay, you can't say that anymore. Okay? Can? Now, this is a short answer to it, of course. Okay, but you can go deeper and say that, okay, transition metals are found after calcium, and therefore the eighth element will no longer be found in the same group as the first element. All right. So I hope you realize that the modern periodic table didn't come out of the blue, okay? It's the work, accumulation of efforts and results from many people. Now, another interesting question to ask ourselves always is, where should hydrogen be placed? And this was actually asked as part of the O level itself. Now, some periodic tables will place hydrogen in group 1. Of course, your periodic table that you use in the exam places hydrogen alone, not under any single group, which is rather interesting. All right. So this question, I will leave it up to you to think on your own. All right. Where should hydrogen be placed? Of course, there are merits and disadvantages with each placement. Some ways, hydrogen is rather similar to group 1. However, there are many ways in which hydrogen is different from group 1. So I would like you to think about it. How is hydrogen similar to group 1? But how is hydrogen also different from group 1? Okay. Now let's go on to the last one, which is on diagonal relationships in the periodic table. Okay. So the diagonal relationships are quite interesting. This uses the modern periodic table. So the periodic table that you use in your textbook, all right, the periodic table that's found in TYS, there seems to be this diagonal relationship. Elements that are linked diagonally seem to have some similarities. Take, for example, lithium and magnesium. Lithium and magnesium have some similarities. Boron and silicon, they also have some similarities. All right. So they told you, for example, boron and silicon are quite similar. Beryllium and aluminium are also quite similar. All right. So now, if you know that beryllium and aluminium are similar, then you now have to decide, beryllium oxide, how will it behave? Now, this we just learned under acids and bases, oxide. So you have learned 4 types of oxides: acidic, basic, amphoteric, and neutral. So beryllium oxide should be similar to aluminium oxide because we just said that they are linked by a diagonal. Beryllium and aluminium are similar. All right. And because they are similar, we need to now ask ourselves, aluminium oxide is an example of which type of oxide? So aluminium oxide is amphoteric. So if you recall from the previous session, we said that amphoteric oxides can dissolve in both acids and bases. So beryllium oxide should also be amphoteric as it is similar to aluminium oxide. Hence, it dissolves in both acids and bases. All right. So this is an interesting property that you have learned. Okay. So next, we move on to boron. So the next question is about boron trioxide, B2O3. Predict the structure present. So when we ask you for structure, we are referring to, is it a giant ionic lattice? Is it a giant molecular lattice? Is it simple molecular lattice? A simple molecular structure, sorry, or a giant metallic lattice? So it's one of the 4. Giant ionic, giant molecular, simple molecular, or giant metallic. So now you have to decide. Again, how do you decide based on this question? You have to know that boron is similar to silicon. They are linked by a diagonal. So boron trioxide is similar to silicon dioxide. Right? Silicon dioxide, boron trioxide. So silicon dioxide, SiO2, you have learned under bonding. SiO2 has a giant molecular lattice structure. So similarly, boron trioxide should also have a giant molecular lattice structure, similar to silicon dioxide. All right. So this is the diagonal rule. Now, once you know that it's diagonal rule, it means that it's giant molecular, therefore B2O3 has a high melting point. So if you recall, our giant molecular, they all have high melting points like graphite, diamond, silicon dioxide, they all have high melting points because they're strong covalent bonds which require a lot of energy to overcome. Okay. Now, for those who just came in from your English ASP, we are now on page 12, I think, of the periodic table notes. All right. Now, and finally, the last one, again, another diagonal, carbon and phosphorus. Okay, so you are told carbon and phosphorus. So this time round, black phosphorus has this structure where each phosphorus is bonded to 3 other phosphorus atoms. Okay, so this is a key word. Each phosphorus bonded to 3 other phosphorus. This reminds you of each carbon bonded to 3 other carbon atoms. This is similar to graphite. So if you recall, right, carbon can exist as 2 different allotropes, graphite or diamond. In graphite, each carbon is bonded to 3 other carbon atoms. Similarly, in black phosphorus, each phosphorus is bonded to 3 other phosphorus atoms. So this is similar to graphite. Therefore, black phosphorus, being similar to graphite, is a good conductor of electricity. Okay. Now, why is it a good conductor of electricity? It's similar to graphite. So the reason is similar. Graphite is a good conductor because graphite contains delocalized electrons between the layers. So similarly, black phosphorus must be the same. It's a good conductor of electricity because it has delocalized electrons between the layers, which are free to move to conduct electricity. Okay, so the benefit of learning periodic table together with bonding is that now you can start to use some of these trends to predict the structure. Once you know the structure of your compound or of your elements, you can predict many properties like melting point, electrical conductivity. Okay? So that brings us to the end of periodic table set number 6. Okay, so later on, if there are any questions you may wish to ask after the session on periodic table. All right. Now, periodic table is one of those topics that you are expected to know and expected to know to quite a deep level for Chemistry Olympiad. All right. Typically, most participants would have been trained on periodic table quite thoroughly. So please do study this set of notes thoroughly as well. Now, moving on, set number 7 is on Introduction to Organic Chemistry. All right, so today we'll begin the introduction to a whole field of study of organic chemistry. So for the Sec 4 students, you would have done this with me in class today, in fact. All right, but we are actually doing the introduction in a sort of a reverse order. Okay, I'll explain later. But for the Sec 3 students, you will not do this until maybe at term 2 or term 3 of Sec 4. So this is really a head start for you. In fact, many of my Sec 4 students, when they took part in Chem O last year, they would have done this as well. I hope they still remember it. Okay. Chemistry Olympiad allows you to have a head start into the topics so that you can learn them better in Sec 4 as well. All right. So moving on, let's move straight to page 2 of set number 7. Okay, I usually begin organic chemistry this way by showing you what the molecules look like. All right. Now, organic chemistry is the study of life-giving molecules. It's the study of molecules found in living things. And as it turns out, many of the molecules in the living things actually contain carbon. All right. So these are just 2 molecules that I've chosen, testosterone and estrogen. So testosterone is the male sex hormone. Estrogen is the female sex hormone. You can see that, right? Actually, it's quite similar, you know, with the exception of a few little differences. All right. Okay, these are some of the differences I've highlighted. Another difference that I would like to highlight is here. Okay, this is one of the differences. But broadly speaking, they are quite similar. All right. But yet, just with a little difference in groups, different ways of connecting the atoms or different atoms, you will now have produced a totally different sex hormone, which obviously results in the differences that you will also see between males and females, right? So from a scientific viewpoint, this is interesting. Actually, there's only 3 elements present in this compound: carbon, hydrogen, oxygen. But yet, they can result in such a wide variety of molecules that gives you the differences between males and females. Okay? And this extends to every single part of animals, plants, bacteria, algae. It really extends. Organic molecules containing carbon form the backbone of all the molecules you will find in all sorts of living things. So why devote so much time to studying just organic molecules containing carbon? Why carbon? Why is carbon even so important? So as I have written, carbon is so common in living things because of 2 main reasons. Number 1, carbon forms 4 covalent bonds. This is something that you learned since bonding. Why 4 bonds? Carbon is from group 4. Okay? Because it's from group 4, it has 4 valence electrons. If it has 4 valence electrons, it needs 4 additional electrons. It needs 4 more electrons to achieve a fully filled outermost electron shell. Therefore, it will form 4 bonds. Okay? Now, this is important. If it can form 4 bonds, that means it can bond to like potentially 4 other atoms. So it can form chains, networks, rings of carbon with other atoms because it's able to form 4 bonds. Now, in contrast, if you think of something like hydrogen, hydrogen can only form 1 single bond, and that's it. So hydrogen cannot form chains. There's no way hydrogen can form chains. Hydrogen is a dead end in a sense because it can only form bonds with 1 single atom. All right. So if you look at the molecules, they really form bonds, many bonds, 4 in total. Each carbon forms 4 bonds in total, right? And that has given rise to rings, chains, networks. And besides that, the carbon-carbon single bonds are strong. Therefore, the molecules that are formed by carbon are stable. Some of you have asked, oh, carbon can form 4 bonds, but so can all the group 4 elements, what? Yeah, but the next element after carbon, silicon. Silicon still can form single bonds with itself, but it's no longer as strong as, say, carbon-carbon bonds. The element after silicon is germanium. Germanium can form bonds with itself, but it's much weaker than, say, silicon or carbon. So silicon, right, you will still see compounds of silicon with silicon single bonds, but germanium, very rare. Okay, you don't have many compounds of germanium where you have germanium single bonds. All right, okay? So this is why carbon is so important, okay? If you were to go on and study medicine, for example, you must do organic chem. And this is the reason why chemistry is the compulsory science subject if you want to study medicine, because many of the molecules in your body are based on carbon. Many medicine, drug molecules are also based on carbon. So without organic chemistry, you wouldn't be able to understand how medicines work. All right? Now, the reason why I said just now we're going to do things in a bit of a reverse order is because usually in your textbook, we will teach you, oh, organic compounds come from crude oil. We need to use fractional distillation to separate crude oil. However, today I'll do a bit of the reverse. Let's just go straight into the terminology and lingo of organic chemistry. And the terminology and lingo is the definitions that I will now do for you, okay? So we are going to go through 3 or 4 different definitions. So let's start first. The first definition we are going to go through is called hydrocarbons. Now, some organic compounds are hydrocarbons. Hydrocarbons, as the name suggests, are organic compounds that contain carbon and hydrogen only. This means that the compound can only have C and H, cannot have other atoms like oxygen, chlorine, cannot. All right, it must be just carbon and hydrogen only. All right, so Later on, we will see some of these compounds which are hydrocarbons. But let's write down the definitions first. So this is on page number 3 of the set 7 notes. So once you're done, please give me a thumbs up so I know I can move on. Okay, so let me just move on. I think the majority of you are done. Okay, so that's the first definition of hydrocarbons. Second definition is important. Homologous series. Now, in periodic table, you have groups. You learn the elements in the same group have the similar chemical properties. Organic compounds don't have a periodic table that lists all of them, but organic compounds can be divided into families, and the families are called homologous series. So a homologous series is a family of organic compounds with the same general formula. So again, we will see what general formula is later. And they have similar chemical properties due to same functional group. Okay, so there's a lot of terminology here, but just copy it down first. We'll go through what it means. And there are gradual trends or changes in physical properties, such as melting and boiling points, flammability. These are physical properties. All right, so a homologous series is a family which has similar chemical properties. So this is similar to groups, right? Elements in the same group have similar chemical properties as well. All right. Now, we use the word similar chemical properties due to same functional group. So what does functional group mean? Now, functional group is an atom or a group of atoms that will give members of a homologous series its characteristic chemical properties. Okay. Now, so now that you have copied down the definitions, we can go back to the previous page to appreciate a little bit more about what we just copied down. All right, so once you have finished copying down the definitions, please give me a thumbs up so I know that you're done. Okay, so we're going to go back to page 3, the flow chart. Now, as part of pure chem, O levels, you are only expected to study these 4 homologous series. So you can see, right, organic compounds can be divided into homologous series, families, right, if you like. And these homologous series, within each homologous series, they will have different organic compounds. So for example, alkanes. Alkanes is a homologous series. Under alkanes, there's methane, ethane, propane, butane, and so on and so forth. Under alcohols, it's another homologous series. You will have methanol, ethanol, propanol, butanol, so on and so forth. All right? So each homologous series contains a number of members. All right? Now, but are all these the homologous series present? Do we really only have 4 families of organic compounds? The answer is, of course, no. Okay, there are many, many, many homologous series, but these 4 are the ones in the O-level syllabus. But later on, you will see more. I've included more in this set of notes, all right? Now, let's go through each homologous series in turn. Alkanes is the first one. Alkane. The name ends in A-N-E. So members of the homologous series, their names must all end in A-N-E. Methane, propane, butane, hexane, octane. So the name has to end in A-N-E for it to be an alkane. All right, so you can recognize it based on the name. Next, they have a general formula. The general formula is CnH2n plus 2. All right. So what is this N? So this is like algebra, right? N must represent something. N always represents the number of carbon. Okay? So the N in the general formula represents the number of carbon atoms, the total number of carbon atoms. So for example, if I say icosane is the name of the alkane, it ends in A-N-E, so you know it's an alkane. All right. Now, ico means 20. 20 what? 20 carbon. So icosane is a 20 carbon alkane. It's an alkane that contains 20 carbon. So N is 20. So icosane is C20H 2N plus 2. So 2 times 20 plus 2. 2 times 20 plus 2, of course, is C20H42. So that's the formula for icosane. Okay? So to find the molecular formula, you sub in the value of N. And the value of N is the number of carbon. N equals to 20 for icosane. So icosane is C20H42. Okay? So alkanes will all follow this general formula. All. So long as it's alkane, it must follow CnH2n plus 2. If it doesn't follow this formula, it's not an alkane. Okay? Now, alkanes have no functional group. Alkane is like the most basic type of organic compound. No special atom, no special group that gives it a specific property or in terms of chemical properties. So alkanes are the most basic, if you like. They don't have a functional group. Alkenes, though, are different. So now we move from alkane, we go to alkene. The name changes, right? So you know that, okay, this is a different homologous series, a different family of organic compounds. All right. Now the general formula is different. CnH2n. So you notice, there's no plus 2 anymore. Why? Because alkenes contain a carbon-carbon double bond. The carbon-carbon double bond is the functional group of alkenes. All right. All alkenes must have one and just one carbon-carbon double bond. So I repeat, all alkenes must have just one carbon-carbon double bond. All right. So even if the alkene has 4 carbon, it only has 1 double bond between the carbon atoms. So later on, we will draw the alkenes out for you to see. Okay? Then you must be wondering, oh, how come alkene is only H2N? Where did the plus 2 go? Maybe a better way to think of the plus 2 is, where was the plus 2 even? Where did the plus 2 hydrogen come from in alkane? If you draw an alkane out, do you realize that there's 2 hydrogens sticking out at the end? So CnH2n plus 2 sticking out. That's why it's 2n plus 2 for an alkane. But for an alkene, because it has a double bond, they don't have the 2 hydrogens coming out at the sides, right? And that's because each carbon only forms 4 bonds. Once the carbon forms a double bond with itself, it can no longer bond to so many hydrogens. Because the limit for each carbon atom is 4 bonds only. The double bond is counted as 2 bonds. Okay, so there's a difference between alkane and alkene. Alkane and alkenes, they have a different functional group, different general formula, different homologous series, meaning they will have different chemical properties. Alkenes will undergo different reactions from alkanes, not the same. Next, but if you take a look at the first definition that we copied down just now, hydrocarbons. Alkanes and alkenes are hydrocarbons because alkanes and alkenes only contain hydrogen and carbon. All right. Now, let me introduce another term here. Alkanes, they are saturated hydrocarbons. Alkenes are unsaturated hydrocarbons. So you might have heard of these words before, saturated, unsaturated, especially if you go out to the supermarket to buy food, for example. You will see that there's some food that's high in saturated fats. So what does saturated mean? Now, saturated actually means there is no carbon-carbon double bond. That means in the entire molecule, there is not a single one carbon-carbon double bond. Don't have any double bonds at all between carbon atoms. Okay? So the unsaturated is the reverse. Unsaturated means there is at least one carbon-carbon double bond. So alkenes are unsaturated because they contain just one carbon-carbon double bond. All right? And then we move on to alcohols. So alcohols are interesting. Alcohol CnH2n plus 1 OH. All right. So the functional group, as you can imagine, is OH. Now, so far you would have learned OH minus. OH minus is part of an ion, right? It's the hydroxide ion. But this is not ionic bonding, it's covalent bonding. So in organic chemistry, we say that the OH group is called the hydroxyl group. So the OH group in organic chemistry is called hydroxyl. Okay? Whereas if it's OH minus ion, it's called hydroxide. Next, we move on to carboxylic acids. Carboxylic acids have an interesting general formula. The general formula is Cn-1 H2n-1 COOH. The question is why? Why is there this -1 here? Why must -1 to the carbon? The reason is because there is already one carbon in the functional group. So whenever you are doing carboxylic acids, you must be very mindful. The functional group is COOH. C double bond O, C single bond O, H. So there's already one carbon present here. That's why you must take Cn-1, H2n-1, COOH. The -1 is because there is already carbon in the functional group. And this functional group, C double bond O, C single bond O, OH, this is called carboxyl group. All right, so you can see that organic chemistry, the terminology might look slightly different from the other branches of chemistry which you have learned so far. Okay, so we go through our alkanes, no functional group. CnH2n plus 2 is the general formula. Alkenes, CnH2n is the general formula. Alkenes have a functional group of carbon-carbon double bond. Alcohols, CnH2n plus 1 OH. The functional group is hydroxyl group. Carboxylic acids, general formula Cn-1, H2n-1, COOH. And the functional group is a carboxyl group. Okay? Now, it might look like a lot to take, but this is a good way to summarize whatever you'll be learning throughout the entire O-level pure chem for organic chemistry. All right. Now, something else to take note of are carboxylic acids. They are acids. They behave like acids, meaning when they dissolve in water, they will dissociate and ionize to produce H+. So carboxylic acids produce H+. So their pH is less than 7. Carboxylic acids will react with carbonates to form salt, water, and carbon dioxide. They also react with base to form salt and water. They also react with metals to form salt and hydrogen. So carboxylic acids are acids. They are just like your other acids which are not organic. Okay? So carboxylic acids are just acids, but they happen to be organic acids. Okay? So now we shall move on to drawing. So can I just check, is everyone okay at this point? If everyone's okay, can you please give me a thumbs up? You've copied everything down. Okay, so we're going to move on to naming and drawing organic compounds. It's not so difficult. You just need to follow a certain convention. So now we're going on page 5. Now, page 5, naming and drawing. So every organic compound has a name. The name can be divided into two parts, the prefix and the suffix. Now, as mentioned just now, the suffix tells you what homologous series it belongs to. So in this case, ane, ethane. Ane is alkane. All right, alkane. Next, the prefix tells you how many carbon atoms it has. So the prefix is either meth, eth, propt, but, pent, and so on. So this corresponds to the number of carbon atoms. Meth is 1 carbon, eth is 2, prop is 3, but is 4, pent is 5, hex is 6, hept 7, oct 8. If you recognize some of these, they are the same as what you use in maths, right? Pentagon, hexagon, heptagon, octagon. I'm not sure if your teachers have taught you. How do you say 9? A 9-sided polygon is called nonagon. So non means 9. Finally, 10. 10 is decagon. So dec is 10 carbons. So a 10-carbon alkane is called decane. All right. But let's draw the simpler ones first. So ethane. Now, ethane has 2 carbons. What's its F? 2 carbons. It's an alkane. So how do I get C2H6 though? I know it's 2 carbons. I know it's alkane, so it's CnH2n plus 2. So C2H. 2 times 2 plus 2 is 6. So C2H6. Okay, so this is the thinking process, and you must think like that before you draw. So it has 2 carbons. I usually draw the carbon first. All right. It's an alkane, so I know there's no functional group. It's all single bond. All right. Next, 2 carbon is a single bond because it's alkane. Then you must know the main concept. The main concept is carbon is group 4. Group 4 must form 4 bonds. I have drawn 1 bond. I need to draw 3 additional bonds. And these are all bonded to H, H, H. Okay, so this is a structure of ethane. So I repeat, you draw the carbon first, the functional group, then you draw the remaining bonds and ensure that every carbon has 4 bonds. All right. So carbon always forms 4 bonds. Cannot be anything else. So when you check your structure later, you must make sure that every carbon atom is surrounded by 4 bonds only. Cannot be 3, cannot be 5. Must be 4. Okay, it's the number of bonds. So how do you count bonds? Bonds you count by the lines. All right. So now let's draw some compounds. Let's draw propane. Propane, pro means 3 carbon. Ane means alkane. So it's a 3 carbon alkane. So it's C3H8. 3 carbon. So I draw the 3 carbon first. I know it's alkane, so it's single bond, single bond. No functional group. There's no OH, there's no double bond. It's just alkane. Then I must make sure I have 4 bonds around each carbon. Carbon on the left needs 3 additional bonds to make it 4. Carbon in the middle already has 1 line, 2 line. So I need 2 more to make it 4. Carbon on the right needs 3 more to make it 4 bonds. Please check that you really have 4 lines, 4 bonds around each carbon. Then you just need to fill up with H, 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 everything. Okay, that's how you draw C3H8. And that's propane. Okay, so later on, I shall leave you to draw butane on your own. Okay, you can try and draw butane on your own. After this lesson, I will fill up the OneNote. You can go in to check whether your butane is correct. But let's move on to the more exciting ones. Let's skip ethene. Let's draw butene. Butene. As the name suggests, butene is an alkene. But suggests it has 4 carbon. It's a 4-carbon alkene. All right. Alkene is CnH2n. Don't have the +2, CnH2n. So it's C4H8. So most students will just anyhow, 8. That means every carbon got 2 hydrogen lah. No, it doesn't work that way. Remember, the first step in drawing any organic compound, once you have the formula, is to lay out the carbon first. 4 carbons. The next step is, after laying out the 4 carbon atoms, you need to know, okay, does it have a functional group? Just now, alkane don't have, so it's all single bond. But alkenes do have a functional group. Alkene must have a carbon-carbon double bond. So one of them must be a double bond. Remember just now I said 1 double bond, not 2, not 3. So even if you have 4 carbons, only 1 of them is a double bond. So now let me choose the one on the right-hand side to be the double bond, okay? We will go through why cannot be the others later on. It can be actually, okay? But let's choose the right-hand side to be the double bond first. Okay, so if the right-hand side is a double bond, the others are single bonds, okay? So please do this first. Lay out the carbon atoms, draw the functional group, then you decide, okay, are they single or double bonds? Next, the rule is that every carbon must have 4 bonds, 4 lines. So the carbon on the leftmost carbon only has 1 bond. You need 3 more. The second carbon, 2 more. The third carbon, how many more bonds do you need to draw? The third carbon has already 1, 2, 3. So the third carbon atom already has 3 bonds, meaning you just draw 1 more. This is where most students will make mistakes. They will just follow the previous carbon atom and just draw 2 lines. It's wrong. You need to count. Make sure carbon has 4 lines. Finally, the last carbon only got 2 lines, so you draw 2 more. So it's H, 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 H. Okay? So this is butene. All right? Having said that, do you honestly think the double bond must be on the right-hand side? Can't the double bond be in the middle? And the answer is yes. What is stopping the 4 carbons from having a double bond in the middle and then single on either side? There is nothing stopping them, right? So this is perfectly possible. If you do your analysis, make sure that every carbon atom got 4 lines around it. You will get this molecule. And this molecule on the right-hand side is still butene. But do you think the one on the left and the one on the right are the same, exact same molecule? I think the answer is obvious, right? Having the double bond at the side versus having the double bond in the middle. It's not the same. It's not the same. All right. So these are called isomers. They are isomers of butene. The first isomer on the left has the double bond at the end. This is called but-1-ene. Why is it called but-1-ene? It's because the 1 means that the double bond is at carbon 1, the first carbon. So this is carbon number 1. So you can number the carbon. So we number it from the end. So number 1 is at the end. Okay, carbon at the end. The second molecule on the right is called but-2-ene. And the 2 in this case means the double bond starts at the second carbon. Okay. Then you must be thinking, oh, then can there be a double bond on the leftmost carbon and call it but-3-ene? Right? Can that be but-3-ene? So let Mr. So quickly draw. Maybe the double bond can be right on the left, right? So this is another possibility, right? However, this is not an isomer. Why? This is because molecules are three-dimensional. You can flip it around. You can flip the whole molecule around, right? So the one I've drawn on top, if I were to flip it from left to right, rotate the molecule left to right, it will be the same as but-1-ene. If I flip the molecule from left to right, the double bond now goes to the rightmost, which is the same as but-1-ene. All right. So the one on top is not an isomer. It's actually the same as but-1-ene. However, but-2-ene, you can be convinced is different because no matter how you flip from left to right, the double bond is in the middle. It's not the same as the double bond at the end. Okay. So we call these two isomers of each other. Can? All right. Okay, if we have finished copying everything here, can you give me a thumbs up? So we're now on butene. So the challenging part, of course, when it comes to isomers is recognizing what is isomers, what are isomers, and what are not isomers. It's not an isomer in this case because when you flip left to right, you get back but-1-ene. So it's the same molecule. If you can get back the same thing, then it's the same molecule. Now, will isomers undergo different chemical reactions? That is a difficult question to answer. It depends on the isomers. So in this case, but-1-ene and but-2-ene, can we agree that they are still alkenes? They are still alkenes because they contain the carbon-carbon double bond. They follow CnH2n general formula. So but-1-ene and but-2-ene, they have the same functional group. They are in the same homologous series. Therefore, but-1-ene and but-2-ene should have similar chemical properties. Okay? So they have similar chemical properties because they have the same functional group, despite being isomers. Now let's move on to the next. Oh, so sorry. Next page got cut off. Oh dear. Okay, never mind. I believe your next page has ethanol and butanol. Let's skip ethanol. Let's go to butanol. So again, you can see from the name, right? All reminds you of alcohol. But means 4 carbon. So you remember what Mr. So just said, but is 4 carbon, all means alcohol. 4 carbon, you must lay out the carbon first. 1, 2, 3, 4. Once you have laid out the carbon, draw the functional group. So this is where you need to think, okay, alkane, no functional group. Alkene, carbon-carbon double bond. Alcohol, what is it? What was the functional group? The functional group is the hydroxyl. the OH. So I will draw the functional group. So I lay the carbon out, then I draw the functional group. I don't rush. Next, once I know the functional group is done, okay, alcohol is the hydroxyl OH. That's it. Right? There's no double bond, nothing, because it's alcohol. Single bond, single bond, single bond. Then I proceed to fill up to ensure that every single carbon has 4 bonds around itself. Okay, so this is the full structural formula of butanol. Full structural formula means you show every single atom and bond present. So this is called the full structural formula. Okay. Okay, so I repeat, draw the carbon out first. Next step, draw the functional group. Last step, then you try to make sure every carbon has 4 bonds. So this is butanol. But then again, you see, hey, Mr. So, how come you draw the OH at the end? Can't the OH be in the middle? Because the answer is yes. The OH could very well be in the middle, right? So I have 4 carbon, 1, 2, 3, 4. Can't the OH be on the second carbon? A bit like how just now butene we had 1 isomer, right? Where the double bond started from the second carbon. So you could reasonably put the OH in the second carbon, right? And that works. Draw my OH functional group. After that, everything else is single bond. Cause it's alcohol, there's no carbon-carbon double bond. Carbon-carbon double bond is alkene, okay? Then I make sure that everything got 4 bonds around itself. Every carbon has 4 bonds around itself. So this is also butanol. But of course, the question comes, do you think the one on the left and the right are the same exact molecule? I think the answer is obvious. Whether the OH is at the end or whether the OH is somewhere in the middle makes a difference. So the one at the end is called butan 1-ol. Again, the 1 because the functional group is at carbon number 1 at the end. Carbon number 1 is at the end, okay? The one on the right is called butan 2-ol. Then you'll be like, oh, then can we have butan 3-ol? Can we attach to carbon number 3 instead? Let's try. Put here, right? So again, can we have butan 3-ol? You got to rotate left to right and think. If I rotated my butan 3-ol, the one at the bottom, left to right, you realize it's not isomer, right? The OH, if it's rotated left to right, the OH goes onto the second carbon. It's the same as butan 2-ol. So what I've drawn at the bottom is still butan 2-ol. Another way to see it is, if you number your carbon atoms, you can start numbering from the left or start numbering from the right. If I start numbering from the right, is 1, or start numbering from the left. 1, 2, 3, 4. So this is also carbon number 2, right? Okay, so that's another way to think about it. Okay, so actually there are only 2 isomers here, butan 1-ol and butan 2-ol. There's no butan 4-ol as well. Not possible. Okay, as a rule of thumb, if you have 4 carbon atoms, your isomers will literally only be on the first carbon or on the second carbon. Unlikely you have isomers on the third or fourth carbon. Okay? Because once you flip around, it will go back to one of the 2. All right. Now, I know I did a very quick introduction on isomerism. All right. This typically takes like 2 or 3 lessons over 1 or 2 weeks of lessons to cover. But I'm just doing a quick introduction. All right. Now, let's move on from butanol. So butanol does have 2 isomers, butan 1-ol, butan 2-ol. The position of the OH group matters. Okay. Having said that, both butan 1-ol and both butan 2-ol, they are still alcohols. So they should have similar chemical properties because they have the same OH functional group. They will have the same chemical properties. All right, moving on. I think another one is propanoic acid. Okay, let's do the last one, propanoic acid. Now this one is tricky. Whenever there's carboxylic acids, I usually tell my students it's quite tricky. You need to be careful. First, you know it's carboxylic acid. This is obvious. Okay, the name literally ends in acid. Next, prop means 3 carbons. And this is where you need to be absolutely very careful. There are 3 carbons. Okay? However, what is the functional group of a carboxylic acid? If you flip back a few pages, page 3, I think, the functional group of a carboxylic acid is C double bond O OH. It is vital that you get this right. The COOH, the carbon is not add on, you know. The COOH carbon is part of the 3. So one of the 3 carbons is in the COOH functional group. Okay? And the rest will be single bonds between the carbon. And the rest is, I think, quite straightforward. And that's why we typically say that propanoic acid is C2H5COOH. Right? Propanoic acid, you must remember, the formula written is usually C2H5COOH. It's not 2 carbon. There's 1 more carbon in the functional group. So my pure chem students, if you recall, there was a similar question like this under energy changes DYS, one of the MCQs, where I went through this specifically. You must be very, very careful when you're dealing with alcohols as well as carboxylic acids. Carboxylic acid is for the carbon. There is 1 carbon atom in your functional group. For alcohol, there's 1 oxygen, 1 hydrogen in the functional group. You must remember that. Okay? Now, with that, we have finished drawing. Now, I'm just going to go on to the next 2 pages and finish there, okay? So, we have learned alkanes, alkenes, alcohols, and carboxylic acids. We have learned how to draw them, name them. We have looked at some isomers, okay, of each of these molecules. All right? But does it mean that organic compounds only have 4 homologous series? Okay, the answer is no. I think at the start I already mentioned this. There are some other common homologous series of organic compounds. Okay, so let me just show you some of them. Now, these are not strictly out of syllabus. So for example, the cycloalkanes question, this question actually came out in one of the year's O-level pure chem. So cycloalkanes, clearly it's not the same thing as alkane, right? If not, we just call it alkanes. Cyclic. It means that the carbon atoms are in a cycle or in a ring. So what is the ring? The ring is here. Cyclopropane has 3 carbon atoms in a ring, a triangle shape, by the way. Cyclobutane, 4 carbons in a ring, a square. 5 carbons, pentagon. 6 carbons, hexagon. So these are the rings. Now, if you count the number of hydrogen, you will be able to get a molecular formula. You will realize that, oh, cyclopropane is C3H6. Cyclobutane, C4H8. Cyclopentane, C5H10. Cyclohexane, C6H12. So I'm sure you realize, quick mathematics will tell you that, okay, the general formula must have N, right? So it's Cn. Then what is H? Cycloalkane, you realize, oh, the hydrogen is double that of carbon. Double, 2N. Then you'll be like, oh, wow. Isn't this the same general formula as alkenes? Right? Alkene, the one with the double bond, is also CnH2n. So does it mean that cycloalkanes are alkenes? They're not, right? Clearly, cycloalkanes are not alkenes. They are, however, isomers of alkenes. And why are they isomers? Because they have the same molecular formula, C4H8, C5H10. They have the same molecular and general formula, but different structural formula. The way the atoms are connected are different. For one, you see that cycloalkanes don't have a double bond, right? Cycloalkanes got no double bond. Okay. Now, another point to note, cycloalkanes have no carbon-carbon double bond. So when you have no double bond, we will call you saturated. So cycloalkanes are still saturated. Whether it's saturated or unsaturated depends on whether it has a carbon-carbon double bond. So cycloalkanes, no carbon-carbon double bond, so it's saturated. Okay. Now, so I gave a little question there. The bond angle between the carbon atoms in cyclopentane is 108. What it means is this angle is 108 degrees. Wow, how did I even get this number? Clearly, it came from mathematics, right? So you have learned the angle, the interior angle of a regular polygon. The formula, of course, is n minus 2 times 180, right? Then divided by n. This tells you the angle, the interior angle of a regular polygon with n sides. So now, can you predict the bond angle between the carbon atoms in cyclopropane? The answer is obvious. Cyclopropane is a triangle. It's an equilateral triangle. So the bond angle is 60. All right. Ken? Now moving on, we have alkynes. Alkynes is the next homologous series. So we have alkanes, alkene, alkyne. So alkyne, okay, I've given you the formula over there. C2H2, C3H4, C4H6. Okay, I hope quick mathematics tells you it's CNH. Clearly it's not N. Okay. It cannot be CNHN, right? C3H4, what? Cannot be the same number of hydrogen and carbon. Doesn't make sense. Clearly it's against some 2N thing. So we have had CnH2n plus 2. That's the alkane. CnH2n is alkene. Alkyne is CnH2n minus 2. Okay? So the general formula is CnH2n minus 2. So we have ethyne. Ethyne has 2 carbons. Propyne, 3 carbons. Butyne, 4 carbons. So again, same thing. 4 carbon, lay it out. All right. Lay out the 4 carbon. Next, what do you think is the functional group for alkyne? Clearly, ethyne has this triple bond. Propyne also has this triple bond. So clearly, there must be a triple bond. The triple bond is the functional group of alkyne. Carbon, carbon, triple bond. So the other ones are single bonds. So the last step is just to fill up with hydrogens to make sure that every carbon has 4 bonds around itself. So it's C3, H4, C4, H6. All right, so butyne looks like this. Again, you must be thinking, oh, but surely the carbon, the triple bond doesn't need to be at the end, right? Surely the triple bond can be in the middle, and you're right. You could draw another version, another isomer of butyne where the triple bond is in the middle. Okay. And then you fill it up with hydrogens to make it 4 bonds. Okay, and this another isomer of butyne. So the first one is called but. Oops, sorry. The first one is called but-1-ine. The second one is but-2-ine. Okay, you notice the number comes in between but-1-ine, but-2-ine. Just like how just now you have but-1-in, but-2-in. Okay, let's press on with the last 2. Okay, I promise I will finish in 5 minutes. Okay, so the next one, we have acyl chlorides. Okay, acyl chlorides are given on the next page. All right, so can I move on? Sorry for the people in this Zoom room. Have you finished copying but-1-ine and but-2-ine? If you have, can you give me a thumbs up so that I know that you're done? Okay, the rest, finish copying. Those who didn't give me a thumbs up. Okay, I'm going to move on now. Acyl chlorides. Now the formula is given to you again. Okay, you can quite clearly see the functional group is C double bond OCl. This is quite similar to just now. You had the carboxylic acid, right? Carboxylic acid is COOH. But instead of OH, you have Cl now. So it's acyl chloride. Another word for acyl chloride is actually acid chloride. They'll be like, oh wow, why call it acid? Okay, but that's another story later on. Now, the general formula quite clearly is related to carboxylic acids. So Mr. So will just give it to you. Okay, so it's Cn minus 1, H2n minus 1, COCl. All right. Remember, N is the number of carbon in total. So the N includes, okay, the carbon includes that one carbon in the functional group. So propanoyl chloride N is 3. Ethanoyl chloride N is 2. Okay, so you must sub in the correct N. Prop means 3 carbons, so N equals to 3. But remembering that one of the carbons is actually in the functional group, okay? But you still sub in N equals to 3. Okay, can? Now next, aldehydes. Aldehydes are interesting also. You might get easily confused. But you see, this is very similar to carboxylic acid, but it's not acid. Why is it not acid? Because now instead of COOH, you have COH. All right. Now, so the general formula, Mr. So just give it to you quickly. Cn minus 1, H2n minus 1, CHO. Okay, so this is how it's usually written. So now you can draw butanol. Butanol is 4 carbons. So 1, 2, 3, 4. All right, then you draw the functional group like that. Then you just have to fill up everything else with hydrogens. Okay, so this is C3H7 CHO. All right. Can? So this brings us to the end, or more or less, of introduction to organic chemistry. I know I have a little bit more left, but a little bit more we can cover in next lesson, together with alkanes as well. All right. So the next lesson will be next Wednesday. Oh, sorry. It cannot be next Wednesday because many of you have the prelim oral exam next Wednesday. So we will delay 1 week. So next Wednesday we will take a break. We will do it the following Wednesday instead. Okay. So instead of doing next Wednesday, which is the 26th of April, we will do the 3rd of May instead. So we will meet on the 3rd of May at 5 p.m. as usual. All right, next Wednesday we can't do it, okay, because many of you will have the prelim oral exams, as well as WA2s are coming up. So please make use of next Wednesday to revise for your WA2s which are upcoming. Okay, with that, thank you so much. I'll stop the recording here.